Hello again. This is section 1.4, Math 204. Okay, so this section starts with Euler's formula. In the notes, it tries to spend some time trying to justify Euler's formula, and because of the desire to avoid some details, it justifies it in a way which is perfectly reasonable, but I think for our purposes it's better to start immediately with the formula. So the formula is for all theta in R, cos of theta plus I sine of theta equals e I theta, and I will often write exp rather than e to the I theta, if only because exp is maybe a little easier to read rather than this. Maybe, perhaps also not the way I've written it here, but anyway. Okay, so the justification for this. Ex times Ey is Ex plus y. Okay, so that auto-focusing stuff should be fixed. Okay, so notice that the thing on top adds, right? And this is related to the logarithm rule. Okay, now similarly, we've seen that the product of two complex numbers ends up adding their angles together. So this kind of looks a bit like this, in the sense that each of these has the x here is theta here, and the phi here is y here. And when you times these things together, just as you're timesing these things together, you end up adding the angles just as you add the angles. Similarly, like this. So this kind of algebraic structure kind of hints that cos theta plus I sine theta should be equal to e to the theta and well, let me explain this. It hints at least that cos theta plus I sine theta should be equal to some thing to some power, which is probably theta, because this isn't specific to the exponential, right? X squared times x3 is x2 plus 3. So the product turning into a plus is not specific to the exponential map. I mean, it does turn out to be related in this way, but if you have x to theta, you can write this as e theta ln x, and then your question becomes, what is that? So what is the ln x when working with complex numbers? Right, so that's an aside to provide some context, and that kind of summarizes the motivation that's provided in the notes, which is pretty good. Okay, so the proof. The proof is, I can only give you an inexact proof of this. So this is not a rigorous proof, and the reason for this is you haven't been told what an exponential of a complex number is. Okay, now I've claimed that it's this up here. That's the statement of the theorem. What is the? We know what the exponent at the exponential of a real number is. It is some sum, Right, I've just looked it up. 1 plus x squared 2 factorial plus x cubed over 3 factorial, and so on. Now you can interpret these as complex numbers, right? You could plug in a complex number here, and we know how to do addition. We know how to do multiplication, so you could work out what the sum is. The real question is, does this infinite series converge to anything when you put in a complex number? And that requires a proof. For x in the complex numbers requires proof. But you haven't been given any proof. Now I could do the definition and then come back to this and rigorously prove it, but I'm not going to. And the reason I'm not going to do that is because they don't do it in the notes. So my assumption is that the people who wrote the notes are both pretty reasonable, sensible fellows, people, and so I'm going to assume that at some point they're going to redress this. So what's the not quite rigorous but kind of rigorous proof here? We take one function, theta equals f of theta equals cos theta plus I sine theta. So f goes from the reals into the complex numbers. I'm going to take a second function, theta g theta, which is exp theta ln x, where x is some unknown, so maybe I could include x in the symbol for g if I wanted to, but anyway. Okay, so first we note that, and that means that g also goes from the reals into the complex. And we note that g of 0 equals e of 0 equals 1, and f of 0 is cos 0 plus I sine 0, which equals 1. So g of 0 equals f of 0. Okay, now this is a little awkward because this hasn't really been defined for you, but I'm going to take the derivative of f with respect to theta, and this is going to be minus sine theta plus I cos theta. So what I've done is I've applied the derivative component-wise to the real and imaginary components of the function f. So I'm ignoring this I, I'm treating it like a constant like you would in the real numbers. Derivative of a constant is 0, so, and the product rule means you get this. Right, and that's minus 1, so that's I squared sine theta plus I cos theta, and if we take the I out, we get I times cos theta plus I sine theta, where I've flipped the terms around, and this is equal to I of the function f, which is interesting. Let's do the same thing for g. We know how to take the derivatives of exponential functions, and if this was real, everything's fine. You know how to do that, but with this complex, it's not so clear that everything works exactly as our intuition from the real numbers says it should. And there's proofs that need to be done there. The truth is that everything does work, so we don't need to worry about it. But yeah. So anyway, the derivative of this with respect to theta is of course ln x e theta ln x, which is equal to ln x g, which is, suspicious. It looks a little bit like the derivative of the exponential function. Okay, so we know that these functions are equal at 0, and we know that they satisfy the same differential equation, except where ln x and I have been put in there. So if we say that, so if ln of x is equal to I, then, right, which is exactly the same differential equation that f satisfies. So together, the equality here and together the same equation for the differential equations implies that f theta equals g theta for all theta. And because we've assumed this, then we get out that cos theta plus I sine theta equals EI theta, which is Euler's formula. So there you go. Now, it's possible, of course, to be more rigorous about this by defining exactly what this is and by defining differentiation first before you come to this. But Euler's formula is a really nice result that illustrates some very nice features of the real numbers. So I think that's why they've I think that's why the notes do it this way. So that's a reasonably rigorous, but not really, because you don't know that the exponential function satisfies the properties that I've used in there. But you know, you can prove those, and if you're interested, go have a look and see. And you know, in a tutorial, ask myself or Glenn about it. Yeah. Okay. Now, so z, an element of complex numbers, can be written as r cos theta plus I sine theta for some r and some theta, and this is of course r e I theta. So that's how the modulus gets in there, right? So that's the modulus, or the value of the modulus of z, and this theta is an argument of z. And we can look at what products of things might look like. So for z equal to r theta I r e I theta, and w equal to s e I phi, the product of these things equals r s e I theta plus phi. And you can prove this by using this equation here. So we want to know what the answer is here, so convert everything back to this form, do the product in the way that we know what it is, and then convert it back to this form, and you'll see that this all works. And so this is kind of nice. I think it's kind of nice. So this brings us to Euler's, where is it? No. This brings us to Euler's identity, which some of you might have seen before. So in particular, e to the I pi is equal to cos of pi plus I sine of pi, which equals ei, which equals minus 1. So another way to write this is ei pi plus 1 equals 0, which you'll see both forms of Euler's identity. Okay, so some people make a really big deal about Euler's identity. And I think when you understand how E is defined, the exponential is defined, and how what the behavior is inside the series that defines ei pi, you'll realize that this is not, well, for me, the exponential explanation is enough not to be amazed by this formula. I think it is a very nice formula, but I think of it as more cute rather than mathematical beauty like some people have claimed. But some people think that this is an amazing thing, and some people have claimed some quite remarkable stuff, so much so that I've printed out the Wikipedia page so that I can read about it in class, because looking it up on your phone is probably a bit passé, right? So the claim is that this is maybe one of the preeminent examples of mathematical beauty, because it contains 0, 1, pi, e, and I, 5 very important numbers in mathematics, and links them all together in a way using addition, and there's a multiplication, and there's an exponentiation. So there's various mathematical operations all built in there, and people think it's amazing. And you might very well also think it's amazing, and if so, good. There's nothing inappropriate about that. Okay, so Stanford mathematics professor Keith Devlin has said this, at least this is on Wikipedia. Like a Shakespearean sonnet that captures the very essence of love, or a painting that brings out the beauty of the human form that is more than just skin deep, Euler's equation reaches down into the very depths of existence. Now, for the record, I don't particularly like Shakespearean sonnets either. I don't understand them. I've tried to read them, and I get bored by them. There are other poems I like more. But Shakespearean sonnets, I don't know. So that gives you an example. That's quite grandiose language, I think, about this equation. Paul Nahin, I hope I'm saying that correctly, a professor emeritus at the University of New Hampshire, says that the identity is of exquisite beauty. Constance Reid, who's a mathematics writer, has, I think, probably correctly claimed that this is the most famous formula in all mathematics. And the quadratic identity is got to be pretty up there, and I think 1 plus 1 is probably better known. 1 plus 1 equals 2, but most famous maybe this. So Benjamin Peirce, who was an American 19th century philosopher, mathematician, and a professor at Harvard, apparently, after proving this identity in a lecture, said that the identity is absolutely paradoxical. We cannot understand it, and we don't know what it means. But we have proved it, and therefore we know it must be truth. I can agree a little bit more with that. I don't really find this equation paradoxical. There's a bunch of definitions, and the definitions combine in a way to give you this equation. I think what all of these people are trying to say is that somehow they're surprised that the definitions capture something of such beauty, or maybe that the equation has a truth in it which seems beyond the definitions. I don't know. Anyway, at the ANU Department of Physics, they have a big poster on the wall. E I theta plus I equals 0, with a whole pile of smoke billowing around it. And it is meant to be, I guess, a demonstration of the ephemeral nature of this, that the understanding of it is fleeting, can only be grasped at rather than had completely. But again, I kind of think the definitions serve quite adequately to explain what this is. And remember, I is rotations, and pi is about a rotation, and I don't think it's particularly remarkable that the angle associated to a rotation might end up, or the value of the angle associated to a rotation might end up being like this. But anyway, more to be said on all that later, I guess. What else? So the Mathematical Intelligencer in 1990 named Euler's identity as the most beautiful theorem in mathematics. And a poll of readers of a popular mathematics magazine may not have seen some of the more impressive mathematics results out there. So in particular, there's two that I think are very good, and I'm going to mention to tell you about. Right, I personally think that two results, one of them called Hilbert's Nullstellensatz and the Sear-Swan theorem, are substantially more beautiful than this. There are some very pretty theorems coming up in this course, and some of those I think are probably more beautiful than this. And it's not that those theorems, there's a very concise nature to this. People kind of immediately understand what this is. They kind of know-ish enough what the components are, at least if they've seen complex numbers. So maybe this is accessible to popular audiences in a way that the other results aren't. But both the Nullstellensatz and the Sear-Swan theorem make statements about how algebra and topology are very closely and tightly linked to each other. If you do topology, or certain forms of topology, and if you do algebra, then in some sense you're studying the same things. Now that's not quite true, but there's a relationship between the two fields that is very deep. And I think I like these theorems more because of the excitement they bring about what they imply, that there's so much more maths. They are like doors to mansions opened up that allow you to wander in and see all sorts of wonderful, interesting things. Whereas Euler's identity doesn't engage me in that way. Maybe the beauty of it has been overblown and talked about at length, that I've become inured to it. But anyway, just my thoughts on that, because I don't know, it's a moment, and you have a slightly non-rigorous but kind of rigorous proof of it. This was nice. I like this. This is also from the Wikipedia page. A study of the brains of 16 mathematicians found that the emotional brain, specifically the medial orbitofrontal cortex, which lights up for beautiful music, poetry, and pictures, so I guess that's not vaporwave then, anyway, that the emotional brain lit up more consistently for Euler's identity than for any other formula. Now, I haven't chased the reference in Wikipedia, but my guess is that they haven't provided other formulas, because to understand both of these theorems, there aren't really formulas associated to this. It's not an equation you write down. These are ideas. I mean, this is an idea too, but expressed as an equation. But these ideas about how other ideas are related to each other and how you convert one idea into another, which is why I think, again, another reason why I think they're very interesting and worth learning about. Nostell-Satz and the Sear-Swan theorem. Right. You can fiddle with this thing in nice ways as long as you're willing to assume certain niceties that perhaps we haven't quite covered. E pi equals E minus I pi, because of course minus I and I times together is 1. And by the normal property of powers, this is ei pi to the power of minus I, which is minus 1 to the power of minus I, which is cute. Have I done that correctly? Yeah, I have. Which is cute. I rather like this kind of expression a bit more, because I think this is a little more weird. We know what the series expansion is for the exponential map. What's the series expansion for this? Yeah, there is one. There is one. So you can define it that way. There is one. Look it up. Look for series expansion of x to the y, if you're interested. Again, you have to prove that certain things converge. Anyway, I think this is kind of cute, and because there's an imaginary number up here, this can be used in a proof. I haven't seen the proof, so I might have the details wrong, but it can be used in a proof that e to the pi is transcendental. My spelling is terrible. Sorry. Anyway, transcendental, meaning that it can't be expressed as that has an infinitely long decimal expansion, right? Isn't that the definition of transcendental? Right. Sorry. Transcendental number, not algebraic, that is, not the root of a non-zero polynomial equation with integer or rational coefficients. Right. So because it's not the root of an algebraic equation, a polynomial equation, that says that somehow the equation can't be calculated by multiplication, addition, division, and taking roots of things. Which I guess is relevant if you want to, what is it, cube the angle, square the angle, whatever it is. Okay. Now this is worth knowing about, because this is an interesting idea. F theta equals ei theta. This takes the real numbers into the complex numbers, and we can ask what the modulus of f theta is. Now, this is the modulus of ei theta, and I implied this before but didn't prove it. So if you think we have the real line, there's my 0, there's pi over 2, pi, 3 pi over 2, here's the complex plane, and we have f that maps between them. It takes 0 to 1, and by definition that's f of pi over 2 is f of pi, f of 3 pi over 2, and I really should draw this right next to it, but I'm kind of don't want to, f 2 pi, because I want to emphasize that. So f takes two values to 1 in the complex plane, and in fact it takes any integer multiple of 2 pi to there, and if you think about it a little bit, you can see it wraps the real line around the circle, and of course the negative bit gets wrapped around as well, which is nice. Here's a thing that you can prove that follows on from all of the similar results that we've given earlier about this. The modulus of an arbitrary z is equal to exponential of the real part of z. Interesting. So how does that work? Ez ex plus iy ex eiy equals ex cos. Well, this is by definition, or Euler's identity. So for when you exponentiate complex numbers, the real part governs how big the thing is. This is the modulus. And the imaginary part governs kind of where you're sitting in an angle around. Right, so you can say the following: the real part of the exponential of a complex number is the exponential of the real part of the number times cos of the imaginary part of the number. Right, that's what this is. And the imaginary part of z equals e rez times sine, that was a terrible sign, sine of the imaginary part of z. Just the same, imaginary part of z, sine e to the x. Right, that is section 1.4.